Actually, carbonate sediment often begins to change as soon as it is deposited, and these changes continue and intensify with burial. As with sandstones, mechanical compaction reduces original porosity, crushing and recrystallizing the weak carbonate grains. At the same time, marine waters rich in dissolved material and trapped within the sediment can further destroy pore space by precipitating a dense carbonate cement. If, however, the rock is uplifted near the surface and circulated with fresh water, a substantial amount of the solid material can be dissolved out, leaving what's known as vuggy or even cavern-type porosity. A major factor controlling what happens to porosity, then, is the composition of the trapped and circulated waters. Of particular importance is the ratio of magnesium to calcium ions in these waters, and that brings us to dolomitization. The formation of dolomite from limestone is caused by the substitution of magnesium for calcium in the general carbonate lattice structure. This process involves a small reduction in rock volume, which acts to increase porosity only slightly, but can increase permeability as much as an order of magnitude or more. Furthermore, because of its tighter crystal structure, dolomite is more brittle than limestone and fractures more easily. Such fracturing, if interconnected, also increases the effective permeability tremendously. For example, the Azmari limestone of the Zagros Mountains in eastern Iran is part of a sedimentary sequence that has been compressed into a striking series of long, linear folds bounded by thrust faults. The folding has created an extensive interconnected fracture system in the limestone. Though matrix permeabilities average only about 10 millidarcies, sustained production rates as high as 80,000 barrels per day have been achieved, and pressure response is essentially instantaneous over tens of kilometers.